In this question, we've got differentiation by first principles to show that dy dx is 4x when y equals 2x squared. So what's really important for us is we have a good understanding of differentiation from first principles. Let's derive it as we go then. I think a picture is really helpful to start off with. So if we imagine a graph with x and y, of course, and we've got some function y of x. So it could look anything we want, but this is good enough. And the problem with this function, y of x, is that we don't know its gradient. But what we can do is approximate it reasonably well. So if we choose a specific value of x, and then we choose another, a little bit further on, another value of x, and what we're saying is that between these two values of x, we've got some difference, and we call that difference h. So if this was x and we've added on h, our next point has to be x plus h. Now let's think about the y values here. Well, if this was x, then the y just has to be f of x. Right, whatever the function of x is, that's what comes out on the y value. So here we've got f of x. And if we then look, we can see how these link together. And if we then look at this point here, where x was now x plus h, well, at this value of y, we have got f brackets x plus h. We put x plus h in, and we've got this function f of x plus h out. Well, even though that this graph is a curve, we could approximate the gradient pretty well by just looking at the straight line between those two, thinking of it as a triangle. Although this is curvy, it's close enough. And remember, if we want to find the gradient, it would be rise over run. So we could say the gradient is rise over run, or sometimes people would write it like this: the change in y divided by the change in x. And thinking about that, well, the change in y, look at our two y values. We've got f of x plus h and f of x. So our change in y here is going to be f of x plus h subtract f of x. And our change in x values is simply x plus h subtract x. So x plus h subtract x. And what this gives us is this: f of x plus h, take away f of x, and these two x's cancel out to just give us h on the bottom. That tells us the gradient, or a rough approximation. But where differentiation comes in is that we've got a limit now. And what this means is that as we make h smaller and smaller, we're bringing these 2 points closer and closer together. That gets us the actual gradient at this exact point when h becomes super small, infinitesimally small. So forgetting about this equals sign here, what we say is that dy dx, that's our gradient. So dy dx is the limit as h goes to 0 here. So h goes to 0 of this thing. So as h becomes infinitesimally small, as h goes to 0, f of x plus h subtract f of x over h, that is our derivative, our first derivative. What we need to do is leverage this then, this definition that we've just derived, to show that when y equals 2x squared, dy by dx is 4x. Let's try it then. We should think about these things. So if y is 2x squared, let's write this down. dy dx will be the limit as h goes to 0 and f of x plus h, so we need our big square brackets, f of x plus h is going to be 2 x plus h squared. 2 lots of x plus h squared. And over here, for the f of x, it's just going to be minus 2x squared. On the bottom, it's always h. So that's the start of how our derivative is going to look from first principles. We can't forget about the limit here. We need to remember this stays. So we still need the limit as h goes to 0. But let's expand out the brackets and see what happens. Well, 2x plus h squared is going to give us 2, we've got x squared plus, and when you think about this, we would have 2xh in the graph, or 2hx, multiplied by 2 should give us 4hx plus 2h squared minus 2x squared. And all of this is going to be over h. So all we did on this line was expand out the brackets from the line above. So now looking at the next line down, we need to remember to keep our limit. The limit as h goes to 0. Well, this is where we can see some nice stuff happening that's going to help us out. 2x squared and a minus 2x squared, they cancel out with each other, they disappeared. Now we should think about the h's on the bottom. Can you see there's an h here and an h here? They cancel out with each other to just leave us a 4x on the top. And if we also thought about that h on the bottom, well, on the top over here we've got an h squared. So that h squared is now just going to become an h. So we've got 4x plus 2h. Okay, well, this is where we should think about what our limit actually means. And as h goes to 0 in this limit, well, 4x is not going to be affected by h going to 0. But this 2h is going to disappear. When h becomes 0, 2h also becomes 0. So this limit actually just leaves us with 4x. That was exactly what we wanted to prove at the start, wasn't it? If y equals 2x squared, dy dx is 4x. We've proved it for ourselves, and to finish off a nice proof, you can often write a square that you've shaded in like so.